Hi, my name is Alexander Savic, one of the architects on the Coherence engineering team. In this presentation, I will talk about new asynchronous name cache API that was introduced in Coherence 12.1. So let's look at a second demo, which is actually a lot more fun than just comparing the numbers in the test. What I did here is we still have the same two cache servers running, and we will load some data into them. And basically what we will load is the content for the coherence.java.net website. So this is Coherence community website. It provides links to a number of sub-projects, open source projects that are related to Coherence that many Coherence customers use and rely on. It also has links to Coherence on Oracle, on main Oracle website, as well as to individual projects on GitHub and java.net. Finally, it has all the events, upcoming past events that we do like Coherence special interest group meetings, as well as an archive of speakers and past presentations. So it has, what's nice about it is it has quite a bit of content so that we can download. For example, it has all these presentations linked as PDF files. So our crawler will have something to do. So it will have to download all the HTML pages, all the style sheets, all the JavaScript files for the site itself, plus all the PDF files that the site is linking to. So let's run the crawler. And first I'll run, I have two implementations of the crawler. One is synchronous, which does everything using old synchronous API and effectively makes the whole thing single-threaded throughout the process. And then we also have the asynchronous crawler, which takes the advantage of the async API and tries to use cluster resources as much as possible. So let's run the sync crawler, and as you'll see, the first thing it will do, it will clear the local cache, and now it's starting to fetch different artifacts. And if we look at the cache server, you will see that both cache servers are fetching different content objects. So while this is crawling the site, and it will take a while, it takes about 2 minutes for it to finish, let's take a look at how this whole thing works. So first we have Coherence cache config. And in this particular case, we have web cache scheme, which stores object with string keys and static content values. And if we look at a scheme for this web cache scheme, you'll see that it runs with 10 threads. It is read-write backing map scheme, and it uses this HTTP cache loader for the given cache name. This cache loader is basically allows us to do read-through. So when we do get request on a cache, it will, if the object is not already there, it will go and fetch it from based on the domain and resource name it is configured with. So for coherence.java.net domain, it will go to the resource that we specify, and we have coherence.java.net defined as a cache name. So what it does is basically uses a Jersey client to simply make a GET request to the target URI. If the status is 200, it reads the binary, it logs on the server that it succeeded, and this is how many bytes the content is, and it creates a new static content instance with the content and the media type of the content. And that's basically all there is to it. And it's actually very, very simple. We also have, in order to serve this, we have, going back to the config, we have proxy scheme that defines HTTP acceptor and defines web server REST Jersey application, web server application, as a root application in the context. So this web server is actually just as simple. All it has is a single endpoint which all the requests go to, and basically gets the domain name from the endpoint as first part of the path, and then after the domain name it gets the endpoint of gets the name of the static resource, defaults to index HTML if it's not there, and then it just fetches gets the cache, gets the static content based on a path from the cache, and if the content is null, returns 404, not found. Otherwise, it renders the content back to the browser. So that's really all there is to it. And all of these three classes are about 180 lines of code or so, and are effectively implementing an HTTP proxy on top of Coherence. So going back here, we can see that the server is finished. They're not doing anything anymore. The crawler finished, and it took about 145 seconds for it to do its job. And the reason it took that long is because it was really doing everything synchronously. It would go and fetch the page, then on the same thread on the client it would parse the page, get the links that the page points to, and then go to each link individually one by one and do the same thing, process them, parse them, etc. So even though we have 2 cache servers and 10 threads on each, which means we have total of 20 threads, we were never using more than one at a time. So the client was effectively single threading the whole application, even though server had a lot more resources that it could use, because server could fetch many of these assets, many of these resources in parallel. So let's do the same thing with the async crawler. And the first thing async crawler does, just like the sync crawler, it will clear the cache to make sure that it loads all the resources again. So let's run it, and as you'll see right away, it will print out everything much faster. Now this is not finished yet, right? I mean, it actually made a request, it parsed all the content, it made a request for all the resources that we need to fetch, and the servers are still working on fetching those, right? And you can see the servers are actually working faster than before, and that will be reflected. And now we are done. An async crawler is done, and it took about 24 seconds. So 145 versus 23, and the code is very much alike, and the functionality is exactly the same. So let's take a look. It's actually going to be easier to do it in the slides and just focus on differences between synchronous and asynchronous implementation of the crawler. So starting from the top, the first line that you have is basically what you would have in your main method. In this case, we just create a new instance of a sync crawler for a given domain, which is coherence.java.net. And we call a crawl method with the root URI, typically index.html. The crawl method will fetch the page for the root URI, and once that's done, the fetch page is recursive method, so it will fetch, process. Once it parses all the links from it, it will call itself recursively and fetch other pages, etc., etc. So once fetch page is done, we will have cache populated, and we can return cache size to get the number of objects, number of resources that we crawled from this specific URI. The bottom example is the same thing implemented using async API. So we're creating async crawler. We're also calling crawl method with the root URI. And the only difference here is that on this crawl method, which as you can see below returns completable future instead of int, we're calling join because we want main to block until this crawler completes. So the crawl method itself calls fetch page, but now fetch page also is not just a method that is void, that returns void. It is a method that returns completable future as well. And when this fetch page method completes, we are calling then apply async and also return cache size. We have to do do it asynchronously here because we're making synchronous call to the cache size method. So in order, coherence requires you cannot mix asynchronous and synchronous calls. So if you want to make synchronous call, you need to make sure that it's executed on a different thread, which is what then apply async ensures. So let's look at the fetch page method in both cases. So synchronous implementation on top basically just calls fetch resource for a given URI if the resource is not null, because we need to guard against cases when the request might return 404. We might have broken links in the page. If the page is not null, then we call process page with the retrieved static content. Similarly, for the async implementation, we call fetch resource, which again returns completable future. Once that future completes, we will call, if the page is null, we will return completed future, which is just a convenience method on the completable future itself to return future that is already completed in case of broken links. Otherwise, if we did get a page, then we will process the page just like in the previous example, and that will return completable future again. So looking at the fetch resource method, the first one is very simple. We're basically just calling get on the cache itself, and that will trigger read through to our cache loader, which will go and make requests to the coherencejava.net to fetch the appropriate HTTP resource. And then in the second example, I'm actually using, for illustration purpose, I'm using instead of doing async get, I'm just doing async invoke on the URI and passing single entry asynchronous processor, just to illustrate that you can actually do a couple of things that you cannot do using just a high-level API. What low-level API, such as single entry asynchronous processor, allows you to do is specify not only the entry processor, as in this case, map entry colon get value, but also whether you want flow control enabled, which is true by default, so we're just repeating that. And finally, the order argument, the order affinity. And this last argument is important because coherence actually ensures ordering of the requests. By default, it will ensure that the requests coming from the same client thread are executed on the same server thread. So by default, you will have ordering between different client-side calls, even though you're using async API. This is very useful, for example, when you're doing gets and puts, because those are cheap operations. Those are simple and cheap operations that tend to perform best when they're executed by the same thread on the server instead of by switching threads, because the cost of context switching is too high when the operation is cheap. On the other hand, we have expensive operations here, and we don't want that behavior. So I'm actually overriding default behavior here by changing thread ID that would be used normally to the hash code of the URI itself, which will ensure that it will be different basically for each URI that I'm trying to invoke. And that will allow this code to actually execute on multiple threads on the server. So instead of executing each request on the same thread on the server, this will allow it to execute on different threads on the server. And finally, we have process page method, which again in a synchronous implementation receives static content. It uses helper method to get local URIs, which actually uses JSoup to parse the HTML and get the list of links from it. It filters the links, etc., etc. So in the end, what we have is a list of URIs that we do want to download. And then for each of those, we basically check if it ends with HTML. We call fetch page recursively and process it just like the original page. Otherwise, we call fetch resource to simply get the resource and load it into the cache. We know that there is no additional processing that needs to be done to it. And the implementation, the asynchronous implementation, is actually quite similar. We get the same thing, local URIs from the page. We have a stream of URIs. The first map operation does the same thing that we did in the if statement above. If the URI ends with HTML, we call fetch page, fetch resource. Remember, in this case, in the async implementation, fetch page and fetch resource both return completable future. And then we collect those completable futures into an array and return completable future all of tasks. And that basically gives us our full implementation. So basically what happens in the async implementation is for a given root URL, like index.html, we will create a tree of completable futures for all the linked pages, CSS files, etc., etc. And we will wait for the root future to complete, and root future will complete once all of the nested, all of the child futures in the subtree are completed. So as you can see, yeah, it is a little bit different than doing things asynchronously, but it is not that much more difficult, and the performance benefits are definitely worth it. And just to show now that we actually have this page working, this is the original site, coherence.java.net, and now let's see what we have locally. So let's 8080. So here is the page loaded from Coherence, and we can go to events. It's all there. We can go to speakers. It's all there. And let's look at some presentations. And this should actually be much faster with Coherence because we have everything locally. And as you can see, opening PDF is instantaneous. And if we do the same thing here, well, it might take a while. As you can see, we're basically serving localhost 8080, coherence.java.net presentations, and we are effectively proxying the Oracle Coherence community presentations page. Which brings us to the end of the presentation. As you could see, Java 8 completable future is really a great addition to the platform. It enables very easy composition of asynchronous tasks. It is much easier to use than any of the concurrency constructs that we had before completable future was introduced. It is somewhat underrated and out of spotlight because of lambdas and streams are so popular and took most of the publicity after Java 8 release. But it is very, very powerful feature. Coherence 12.2.1 adds completely new asynchronous name cache API that is based on combination of completable future and low-level features that Coherence itself provides, such as asynchronous entry processors and asynchronous aggregators. And as you could see from the examples, it is much easier to use than if you had to use low-level features directly. Bulk read operations also support streaming mode, which gives you better performance and reduced memory usage on both server and the client. I hope you've enjoyed the presentation and you will enjoy using the async name cache API in your next application. Feel free to post any questions or feedback in the comment section for this video, or reach out to us via one of the following social media channels. Thank you.